So in this lecture, we are going to study various operating system scheduling policies. So what is a scheduling policy? It is the piece of code that basically decides which process to run next. Once you've decided you need to context switch, which of the many ready processes should I run next, right? And what the operating system really schedules are what are called CPU bursts of a process. That is, when a process comes for execution, it runs for a certain continuous duration of time on the CPU before it either exits or goes to wait for IO or whatever, right? So the duration of time for which it continuously runs on the CPU, that is called a CPU burst of a process. And the scheduler basically schedules these CPU bursts on the available CPUs of the machine. And a scheduler in general has certain goals that it's trying to optimize, right? Of course, it tries to maximize the utilization of the CPU. That is, it tries to make sure the CPU is fully used as far as possible. And it tries to minimize the turnaround time of processes. So that is, from the time a process is created and comes into the system to the time it completes execution. This is called the turnaround time, the start to end of a process. It basically tries to minimize this, make sure processes are not waiting too much. And it also tries to minimize the response time of a process. So the response time is slightly different from the turnaround time. The response time is the time from the process arrival to its first scheduling, right? So the response time is basically what gives you the interactivity. So once a process starts running, it starts to generate some output and the user can perceive that something is happening, right? And the turnaround time is the time from arrival to completion, whereas response time is arrival to beginning execution. And a scheduler should also try to be fair. It should make sure that all processes get their turn eventually, and it should also try to minimize overhead. So what is overhead? Every time you decide to context switch, go from one process to the other, you're incurring a certain overhead. On modern systems, if you want to switch between processes, it takes like around a microsecond, less than a microsecond, a little less than a microsecond, right? Because you have to move all the mechanism of the context switch that we discussed. All of that takes some time. And you want to minimize this overhead, right? You don't want to be switching around processes way too much. And you want to amortize the cost of this context switch for a long enough period of time by running a process that you've switched to for a long enough period of time. So these are all the goals of a scheduling policy. So we are going to see a few simple scheduling policies, starting with, of course, the easiest is FIFO, first in, first out. You take all the ready processes in your system, keep them in a linked list and start scheduling processes from the beginning of the queue. So in our, suppose 3 processes A, B, C arrive at the time t equal to 0 and in the order A, B, C, right? And they are all placed in a queue. And you schedule process A first, then you schedule process B next, and you schedule process C next, right? So this timeline here shows process A running, followed by process B, followed by process C. So this is a simple FIFO schedule, right? It cannot get simpler than this. So why is this bad? What are the problems with it? One main issue is what is called the convoy effect. That is, sometimes you get stuck behind a really long fat process and your turnaround time is really bad. Now here process B arrived just at time t equal to 0, just behind A, but it has to wait for a long time until A finishes. So B is not happy about this, right? So FIFO tends to have this issue. So how do you fix this? Another simple policy is what is called the shortest job first policy, right? So when A, B, C all have arrived together, it makes sense to finish B and C first, right? Because their turnaround time is going to be really small now. Get them out of the way and then start your long process, right? And when you do this, you can actually prove that this is optimal. It optimizes, it minimizes the average turnaround time of processes, right? So this is the good thing about shortest job first. But note that this is a non-preemptive policy. That is, it's not really useful in a situation like this. A is already starting to run and B, C arrive here at this point. They arrive. So then they are still very short jobs, right? and they should still be done soon, but still they have to wait until A finishes execution. Why? Because shortest job first does not preempt A, does not stop A as long as it wants to run. So the next logical path to go is a preemptive version of shortest job first. This is called the shortest time to completion first or shortest remaining time first. So this is again straightforward. It is simply a preemptive version of shortest job first. So here when B and C arrive and A is running, you compare the remaining time of A with the remaining time of B and C, and you see that okay, B and C are shorter, therefore you schedule them first, right? You calculate the time left of a process, and if the time left of a process is really high, you go ahead, preempt it, and you favor shorter jobs. And finally, another simple policy is round robin. It is fairly straightforward. You put all the list of processes in a queue. So this is also a preemptive policy. You put all the list of processes in a queue and you execute the first process for some time, then the next process, then the next process, then the next process, and you come back to the first process, right? So every process runs for a fixed quantum. So this can be a millisecond at 10 milliseconds or smaller than a millisecond and so on. So it cannot be really small. You cannot run one process for a microsecond, the next for another microsecond, right? Because it takes you a microsecond to even switch. So once you switch, you want to run it for a reasonable amount of time. So these typical quantum time slice values are around a millisecond. That is when the overhead of the context switch is amortized. So what is the good thing about round robin? It is good for response time, right? Because you don't have to wait for another big process to finish ever, because every guy will get their turn. A small slice here, a small slice here, right? So here you can see this is shortest job first. A runs, then B runs, then C runs. So B and C have really huge response time, right? So B has such a high response time. C has this huge response time. Well, actually it doesn't go all the way from here. The response time of C is from the time it arrives to the time it is first scheduled, and this is the response time of B. These are really huge values, right? It takes a while before you can start seeing any output from the process. But with round robin, A runs for a short period, then B, then C. The response time of B and C is really small. As soon as they've come, they get their tiny quantum slice almost immediately. So round robin is good for response times, but it is not that great for turnaround time. Why? Because the execution of a process is really dragged on, right? You have to take turns with everyone. Therefore, it's not great for turnaround time, but it is also good for fairness. Everybody gets their turn, right? So this is a very simple policy. As you can see, there's no one right answer, right? Each policy, some policy, shortest job first is good for turnaround time, round robin is good for response time, and so on. So depending on what the goals of your operating system are, you will pick a suitable scheduling policy. And in real life, schedulers are a little more complex. They don't use just one of these simple policies. In fact, the real life scheduling policies are some combination of all of these things. For example, Linux uses what is called a multi-level feedback queue or MLFQ. So how does MLFQ work? You have multiple queues of processes, right? So this is one queue of processes, and this is another queue, and this is another queue, right? And these are different queues of processes with different priority levels, right? So the queues on the top have highest priority, queues on the bottom have lowest priority. And you always pick processes from the highest priority queue. If there are no processes here, you go to the next queue, you go to the next queue, and so on, right? You pick based on priority. And then within the same priority, you can run any algorithm like round robin to go over all the processes of a given priority. So how is this priority fixed? Different implementations do different things. For example, one way to think about it is when a process enters, it has very high priority. You place it in the highest queue. But once you see that it's using a lot of CPU, you might decide, let me lower its priority a little bit. After some time, its priority goes down even more, and so on, right? Priority could decay with age. That is one way. Or the user could set the priority of processes. Linux has a command line argument where you can set the priority of processes, and that could be used to decide priority. There are different ways in which you can do it. But as you can see, this is one sample of how real life schedulers work. They use a combination of, here you're using priority scheduling and round robin and a mix of different ideas to make it work in real life settings.